Okay, so first we are going to check your solutions for the homework. I have not checked if you uploaded any of your solutions. Okay, now I can see that 4 of you uploaded them. Let me share my screen. Okay, and here are your solutions. So Rashid, Ahmed, Islam, and Danny uploaded their solutions. Okay, first of all, have you did you have any problem with solving the homework?
No.
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 Okay, so Rashid, can you hear us?
Yes.
Do you allow me to look into your solution and show it to to your fellow students?
Yeah, okay.
Thanks. Okay. So this was the homework, right? So we had
Sorry,
this.
I can't see your screen. I can't.
You can't.
It just turned.
Well,
It's fine for us.
yeah, it seems
Yes.
fine for me as well.
Sure.
Yeah, so this was the homework. I gave you a formula and this was the question, is if it is satisfiable or logical or a contradiction. And you have to solve this with using a truth table. Okay, so here is the truth table. Okay, let's see. So we have two variables, x and y. Okay, and well, you introduced several columns because I guess you wanted to do this step by step. Okay, here are the 4 interpretations. Yes, exactly. So speaking of this implication, it's quite clear that it is false only in the last row because here not x is true and y is false. Okay, that's fine. Then you negate this column. This is how you get 0, 0, 0, 1. Finally, you connect not x and not y with conjunction. Exactly. And finally, you take these two columns here, and take the XOR of those two. Exactly. So they are in all interpretations, those two columns are the same. Therefore, the XOR must be false at the end. Therefore, as you just say here, it's the formula is a logical contradiction, unsatisfiable. Nice.
But why did
I think I have different.
Yeah, me too. Why did he connect
logical.
the not X and the not Y?
So as far as I can see, this was the original formula I gave you.
Yeah.
So how should we do this in other way? What? Okay, may I open your solution?
Yeah, sure.
Who are you?
Danny.
Danny. Okay, Danny. So here is your solution. Okay, Danny did the same actually.
But I got different results.
Okay, let's see. So we have he introduced this notation A for the left-hand side of the XOR. Just a minute. Yeah, let's see if it is the same as in Rashid's solution. 1 1. Okay. No, it's completely different. No, 1 1 1. Interesting. So here, when x and y are both true, the implication not x implies y is true. So this is true. Then you have to negate it.
Negate it, false.
So this should be false here. For example, am I right?
Yes.
Yes.
Okay, so this is a mistake. Then also in the next row, x is true, so not x is false. Then the implication is true.
I think I added the outside negation before doing the implication. Yeah, that was the mistake.
Okay, okay. Yeah. Actually, this is okay. This is not okay. So this should be false. Exactly. Okay, and then B. So B is easy. It's a conjunction. So it's kind of sure that it cannot be false all the time. So not X. So there is only one difference in the last row. So in this row, okay, you made another mistake. So the last interpretation should be 0 0.
Oh yes.
Okay. So if both x and y 0, then not x and not y are both true. So the conjunction of them must be true. And now here we are. So the values of a and b are the same. Therefore, the XOR of those two must be false everywhere. Everywhere. This should be false. This should be false, and so on. You understand what I mean?
Yeah, yeah.
Okay. So who got who no. Some of you told me he got a different solution. Who was that?
It was me.
Oleg. Okay.
But I didn't send you.
Okay. I see.
And I ask you a question in chat.
Okay, go ahead. Yeah, what's the question?
Oh, it's in chat.
Oh, in chat. Okay. Yeah, I see. Yeah, that's the good question. Exactly. In what order to evaluate the formula, and basically you asking, do you have to evaluate the XOR first before the conjunction, or the conjunction first?
Because I evaluated it the XOR first.
Yes, I see. Actually, I thought this will be the most common problem for all of you, because I intentionally didn't put a parenthesis here. So you have to know which operator is stronger. I mean, which has the highest precedence. Which one? XOR or conjunction? Which one has the higher precedence?
XOR, I think.
No.
Conjunction.
No,
Conjunction
that's
is,
conjunction. Yeah.
so basically this is the correct order of evaluation. You have to evaluate conjunction first, then XOR,
Yeah.
as Rashid did.
That's why I have another answer.
Exactly. Yeah. That's it. So you should also know what the precedence of the operators are. Otherwise, you can get a completely wrong solution, wrong result. So here is the table of operators precedence, and as you can see, conjunction and disjunction are before XOR. So they are stronger. They have higher precedence, sorry. Okay, do you understand that?
Professor, I want to know, I uploaded the assignment, but I don't know if I did it right or wrong.
So you uploaded it. What's your name?
Ahmed.
Ahmed. Okay, I see.
By the way, sorry for not attending yesterday.
Mm-hmm.
I had
did you go to the immigration office? Okay.
Yeah.
And everything was fine?
Yeah, thanks God.
You get your permit or?
Yeah, I get it, but I still have to get my tax card, TAG card.
Yeah, okay. So do you know how long does it take to get these cards?
The good thing is that they don't require an appointment. I can just go and just sit for half an hour to get it, but the problem is they still would have an hour because I still have to find a gap between the courses.
Okay, I see. So if you can fetch your cards soon, it's still okay, I guess.
Yes.
When I was a student at university, I spent 1 year in Greece. I worked there at the university as a researcher.
Yeah.
So I spent 1 year there, and I received my card for healthcare after 1 year.
Yeah.
So actually, I was about to leave Greece when I fetched my card. It was really crazy.
Yeah.
So it seems Hungary is a little bit better than that. Let's hope so.
Yeah.
Okay, so here is Ahmed's solution, and you got different results in the second row. So let's see. So yeah, here I can see some problem. So now x in this row is 1, therefore not x should be false. Am I right? So here. And similarly, y is, what? I don't get this. Why do you?
No, I split it like the whole parenthesis of not x amplified to y was 1. So this is a whole term.
Okay. So 0 is the value of this implication then? Sorry.
Yeah, the whole one was 1.
Okay, so not x is 0 now, so I don't, then the implication is true, so you negate it, so you get 0, right? Exactly, so on the right hand side, not x and not y is now false. What? So not x is 0 in this row, not x is 0, therefore this conjunction should be false.
Oh, this might be the problem here.
Okay.
Okay.
0.
Yeah, but I don't understand what is this in front. So this, what is this 0? What does it stand for?
Not the whole parenthesis, the not for it. So it's 0 outside.
So you mean you basically negate the whole expression like this?
No, it was just for the first one without the bigger parenthesis.
Okay.
Yeah, this like this.
Yeah. So this was the problem here. Then this should be 0, right?
Okay.
Okay. Yeah, it's really easy to make a mistake. One slight mistake and you got a completely wrong result. So this is why I actually hate truth tables. It's so tedious to fill those tables and it's so easy to make a mistake. If you were right, then yes, the result would be correct. So it would be satisfiable, but you made a mistake. So it's unsatisfiable. Okay, do you have any other question? Nope.
No.
Okay. Okay, then let's continue with the next topic. In the yesterday's lecture, I talked you about certain rewrite rules. So
I'm sorry.
excuse me?
Could you please check my solution?
Yeah, okay, no problem. Yeah, it seems all right. If we compare it with Rashid's solution, where is it? Where is Rashid's solution? He got 1, 1 in the interpretation 0, 0, and you did this. You had the same result here. In this interpretation, you get 1, 1, and finally you use XOR, and you prove that the formula is unsatisfied. Is what? No, it's not a logic. Excuse me?
Yeah, the result is not correct.
It's not correct. I mean, the result in the table is correct.
Yeah.
Formula is always false, but this means it's unsatisfiable. Unsatisfiable. And it's not a logical law. Islam, do you agree? Or you don't agree? Yeah, I can hear you. You are very, very, how to say?
I agree with you, yes.
Okay. Okay, this was the only mistake at the end, but the main part was all right. Okay, so as I mentioned, yesterday we learned about some rules, some laws, which we can use to simplify our formulas. And after simplification, we can check those questions, those semantic properties, if the formula is a logical law or tautology or satisfiable or unsatisfiable. So this is what we try now with this formula. So we will solve the same exercise, but by not using a truth table, but simply we try to simplify this formula, and then we will see what result we get. Okay. Okay, so if you are with me, I will continue with in a separated Google document. Okay, so the question is the same. But now we will solve it in a different way. So here is the formula. And let's simplify it. So first of all, such operators as XOR or implication should be eliminated completely. This is very important. So first of all, we should transform the formula in order to get only negations, conjunctions, and disjunctions, nothing else. We have to completely eliminate all other types of operators. So for this, we learned yesterday certain rules, rewrite rules, how you can eliminate an XOR, for example, in the very first law. Okay, so this is what we are going to apply. We just rewrite it to negated equivalence. Okay, let me copy this formula. And I'm going to switch from XOR to equivalence. And what else? What else do I need?
Simplify negation. Equivalence.
Equivalence. So we have to negate all this formula, all this equivalence. Therefore, we have to introduce a new pair of parentheses, first of all, and we have to put negation in front. Okay, thanks. Can I use coloring here? No. Okay, anyway. So
this is the typing color.
Excuse me?
This is the typing color. That's the color you type with.
Yeah, I tried this first, this highlight color, but it doesn't work either. Okay, so what's next? So the next step is, removing equivalence. This is also, so to say, prohibited. So this is how you can rewrite equivalence. Basically, you repeat the same formula and replace equivalence with implication, and you use logical AND between. So it's a back and forth implication, basically. So this will make the formula really, really ugly. And, well, yeah, so it will be much more uglier than it was before.
What if we started with the other things, make it like simple, and then we can use the XOR?
Yeah, okay, let's do it. So what do you suggest?
Negation. Started with simplify negation.
The negation of the implication first, and then.
So this one.
Yeah.
Yes.
Okay. So do you remember how we can transform this?
Morgan laws.
How?
Morgan laws.
De Morgan.
With rewriting implications.
Yeah, first, the De Morgan rules can only be used if you have either conjunction on
okay.
disjunction
Yeah,
in the
yeah.
parentheses. Now you still have
Yeah.
implications. So yes, you are right. First, we have to remove. I mean, what is this? Eliminate the implication, like that one.
So it will be X or
Mhm.
Y.
Exactly. Yeah, that's it. So X or Y.
We
Okay.
can also add the negation from the outer. It will be negation X and negation Y.
So you are talking about this one. We are trying to transform this part of the formula, right?
Yes.
Now I see what you are doing. So this is
Negation X and negation Y.
yeah. Here we apply one of the De Morgan rules. Exactly. Okay. So what now?
I think now we can like simplify the XOR. There's also more.
Well, just look at the
We
formula.
can eliminate the equivalence.
Yes. Yes. Why?
Because it's also all the time equivalent.
Yes. Because the left-hand side and the right-hand side are the same, no? Right?
Yeah.
Yeah, exactly. So that is such a very obvious rule.
Equal one.
Yeah, everything is equivalent with with itself. Exactly. So you can simplify this to 1. Exactly.
So at the end we will get 0.
That's it. That's it. Nice work. Okay, I made a mistake. I eliminated XOR first, but anyway, finally we get 0. That's it. Nice. Very nice.
Easy way.
Yeah, this was the easy way and the smart way. So you are right. Actually, eliminating the equivalence is always a pain in the A, because it makes the formula so huge. Actually, it doubles the formula size, as you can see. So you are right. It's better if we postpone the rewriting of equivalences as far as we can. Good point. Okay, nice. Okay, so this is another way to solve this type of exercises, to use rewrite rules and simplifications in a smart way. This is the smart way. The truth table is the dumb way or dummy way. Okay. Any question at the end?
So for the transform the formula in order to get the only negation, conjunction, and disjunction. So this only works with the formula that will be unsatisfiable, because at the end we only get one possibility, which is 0.
Yes. So we showed that the formula is always false. Actually,
so for example, if I tried doing this with logical law, it won't work, right?
So if you get 0 at the end, it's unsatisfiable. What should you get?
No, for example, if the equation is logical law, I mean satisfiable, which means that there is at least one true. This means that simplifying it won't work.
1, yeah. The result, I think it's 1.
Well, for satisfiable formulas, the result won't be 0 or 1. It will be. It would be some. The result would
at least
contain variables like x or y, something like that. Okay, let's see such an example. Okay. Okay, if you get 1 at the end, it's a logical law. the question is now, when is a formula satisfiable? How we can know after simplification, after the simplifications? So let's see such a exercise. This was your question about? I hope so.
Yes, yes. How we can know at the end after simplifying it that the formula might be satisfied.
Okay. Let's see such a exercise. Okay, let me find some exercise here. Maybe I can find one. Just a sec. Okay, so for example, just a minute. Okay, so here is a form. Here comes the formula. Negation, parenthesis, A or not B implies. Why I'm typing so much? No. Implies what? Implies C and B. Then implication and negation A and sorry, not A and B, and at the end I would like to put everything in a parenthesis and negate it. It looks so ugly. Let me put some spaces between. Sorry, no, it's not good, not okay. Sorry for that. Let's use here, instead of not A and B, we should use A or not B. So if everything is okay, this formula should be satisfiable. I think so. This is what we are going to prove. Exactly. Okay, so how to start?
Start from the left implication, negation B, implication C.
So this one, the left.
Yeah, we get rid of it.
Okay. Okay, let's do this. So how we can get rid of this? How can we get rid of this implication?
Negation A or B.
Yeah, so you are about to negate the left-hand side of the implication.
Yes.
Yeah, and so this is how you get negation A
and B.
And this is important. You have to change the or to and as well. As you remember, this is what the De Morgan rules are about. Okay, and what to do with the implication?
Or.
Okay. And here there is a problem. So we have conjunction and disjunction on the same level. it does matter in what order we evaluate them. Therefore, you have to keep this information here that this left hand side should be evaluated first. Therefore, I use an extra pair of parentheses. If you don't put a pair of parentheses there, it's not defined in what order to evaluate the and the or. Okay, how to continue? What would you do in the next step?
Negation in the first part.
I would do the same. Implication?
Yes.
Yes. Let's get rid of this implication here. Okay, so I guess this implication turns into logical OR as before. And what to do with the left-hand side? We have to negate it. So how to negate it in a very easy way?
Delete one negation.
Excuse me?
Delete one negation.
Which one?
Change one. The first one.
We can remove the outer, the very outer negation.
Yeah.
The very outer, this one?
Yes,
no.
And we can add it only to the right side.
Yeah, but first we have to finish the transformation which comes from this implication. So we definitely must negate the left hand side of the implication like that. And now you can think about what to do with these huge number of negations. Should we apply De Morgan laws or not? Or, and here comes your suggestion, which was about?
Yeah, just remove this one and make it and then add the negation to the right side.
Okay, you would delete the outermost negation.
Yes.
Okay. Okay,
And in the middle, instead of or, it will be and.
Yeah.
This one, yes. And then negation of the right side.
Not only on the right side, but also on the left-hand side. So you have to remove this negation and that negation as well. So you have to negate both sides.
Yes.
Yeah, and don't forget to put a pair of parentheses here, otherwise we have the same problem with this conjunction, disjunction. Okay, so it became a little bit complicated how we solve this, how we are solving this exercise, but I think we are on the right track. Do you have any question meanwhile?
No.
I hope you could follow it, because it became a little bit more complicated as I planned. After we finish with on this track, I will show you how you could start the whole stuff in a simpler way. But anyway, let's finish this solution first. So now what? Now we have, if you look at the formula, we have conjunctions as main operators, and the conjunctions connect this one with B and that one. So B and A or not B cannot be simplified further, but the very first part could. How to do that?
Should add the negation.
Oh, excuse me?
We get rid of the outer negation?
Yes, we get rid of the outer negation. Again, we are going to apply one of the De Morgan rules, De Morgan laws, sorry. Oh. Okay, so what do we get here?
A or B, or negation B.
Ah, very nice. So basically you flip everything to the opposite inside. Really nice. So you get A here, or there, negation here.
And negation
And
C.
negation C.
That's it. Nice. Okay, and we can remove this parenthesis. So now we have 5 expression connected with logical and 4. Okay, so this is what we get. Can it be simplified?
I think A or negation B, we can do something, but I don't know what to do with it.
Yeah, we can do. Yeah, exactly. So what to do with this part? Which we have
They're
to...
equivalent, I think.
Excuse me?
We can change it to equivalence, I think.
C.
Can we do that?
No. So just look at the formula. We have A or not B twice.
Twice.
Why do we need it twice? We don't. So
Remove 1.
yes. This is also based on one of the rules, which we called idempotence. So if you have a logical and logical or, you can just remove duplications. Okay. It's kind of logical, of course. So you can remove duplications after you only have logical and logical or and negation. And okay, so this is what we get at the end. Well, I'm not sure we can simplify this further. Or we can try. So I mean, typically, once you cannot do anything, any simplification anymore, sometimes you will see such, how to say, something like that. So, for example, B appears here and there as well, but they are not really connected to each other. But you can make them connected. So you can make not B and B connected somehow. Let me reorganize this formula. Maybe it will be easier to see the possibilities here. So maybe we can work on this side of the formula, B and A or not B.
We can add negation.
What can we do?
Add negation.
No.
And simplify by negation, another negation.
You cannot add stuff to the formula. You have to keep,
Yes.
how to say, you always have to transform the formula to the equivalent formula. So if I add a negation, for example, here, it won't be equivalent with the original formula anymore. But maybe your suggestion was something about something else. I don't know. Okay, so this is not that obvious now. If we can simplify this formula, let me show you how we can use now the law of distributivity, VT, which is a kind of ugly rule. I was talking about it in the lecture. So this is it. If you have a formula of this form, so something is conjuncted with a disjunction, and actually we do have such a part of the formula, then we can we can transform it to a disjunction of conjunctions. So let's try this. Let's try to transform this part of the formula. So let's transform this part of the formula to what? Can you help me?
B and A.
That's it? Exactly. So this
Or
is, yeah,
B and
B and not B.
negation B.
that's it. Exactly. So this is what we got.
What
And
the
yeah,
is 0.
yeah, and this part B and not B is always 0. It's always false. We have such a law. It is called non-contradiction. It says that if something and the opposite of that something, I mean, they cannot contradict. They contradict to each other, so there is no other choice. Anyway, this part is 0, as you just told us. Yeah.
And we can simplify this one also. We can make it 0 because
Not 0. B and
Exactly. So if one of the operands of logical OR is 0, then the other part of the formula will, how to say, you have to evaluate the other part of the formula, and this makes the result actually. So basically, this is what you get here. We have such a law here. Something ORed with a 0, it's equivalent with that something with P. So this is what I use now. What we use now. Okay. Did you get all of this?
yes.
Actually, you were really you were completely right. Okay, and now let's substitute this part of the formula with B and A, and now you can see that we get a beautiful formula at the end. B and A and C and not C. So this is the final result. This is the simplest form of this formula. You cannot simplify it further. There are no duplications inside, so there is no hope to simplify this further. You cannot simplify it 1, you cannot simplify it 0. This means this is a satisfiable, I mean the original formula is a satisfiable formula. So this is how a satisfiable formula looks like. Okay. So this is satisfiable. Okay, of course we can think about what does satisfiability means. It means that we have to show that this formula can be true, and you can just find truth values for B. So if you substitute one for to B, 1 for A, and 0 for C, then the whole formula becomes 1. So basically this is the interpretation which makes this formula true. Therefore this is a satisfiable formula. Okay. Okay, so maybe you have some question.
Yes, about the distributivity law. Before using it, there are only two different symbols, which are B and parentheses A or negation B, right?
Yes.
So at the law, there are three different ones. So does it really make difference?
No, I mean, this means that the
DQ and R.
yeah.
But here we only have A and B.
Yes. No, it doesn't make any difference. It doesn't make any difference now. It just means that this law P in this law, this P and Q or R works as a template, so you can substitute anything to P, anything to Q, and anything to R. You can substitute 3 different formulas into those 3 letters, or you can substitute the same if you want. So it's no problem if you substitute the same to them.
Oh, okay.
Okay, any other question? Okay, I'm telling you that the law of distributivity is always the bad guy. I mean, you don't typically you don't want to apply it because it makes the formula much longer, especially if there are several elements inside your parentheses. The formula grows in a very drastic way. So it doesn't feel good to apply distributivity, but sometimes it pays off, just like now. But for this, you really have to, how to say, it's a good idea to postpone the application of distributivity as long as you can, and after you are at the point that you cannot do anything further, then you might want to try distributivity if it is work, or if it does work, or if it does not. Okay, then let's move on. For today, I have a brand new topic for you, which is based on the same laws. So we keep applying those laws for a completely different purpose. And this is about transforming your formulas to nice forms. We call those nice forms normal forms. Okay, so these are the aims of translating formulas to normal forms. Basically, we want to evaluate our formulas easier. We want to make them more transparent. If you look at the example here, so if you look at the original formula, it's a complete mess. It's hard to see how to evaluate it, what truth values to substitute to A and B and C, what makes the formula true. But after you transform the formula and you get this one, the very last formula, you can just look at it and see what's the situation. It's so easy to evaluate and so easy to find an interpretation. So those normal forms have a similar purpose, similar aim. And also those normal forms, CNF and DNF, this is how we call them, are used as standard input formats for certain softwares we are going to use. Actually, you are going to learn about normal forms not only in logic, but in other areas of computer science. For example, in databases, you are going to learn about certain normal forms. In logic, there are several normal forms, but CNF and DNF are the most common ones. So this is why we are going to learn about CNF and DNF. Okay, so this is the next topic. CNF. NF stands for normal form. So the question is now what C stands for and what D stands for. it's kind of easy to figure this out. So CNF stands for conjunction, and D stands for disjunction, and the name of the normal form is not disjunction normal form, but disjunctive normal form. Similar, conjunctive normal form and disjunctive normal form. But anyway, they have something to do with disjunction and conjunction. So it's easy to understand both of them. Let me just give you a short introduction. In the lecture, I will talk so much about DNF and CNF. For example, I will give the exact definition of both two. But now it's completely okay to understand what they are in a practical way. So CNF, you can imagine CNF as a formula with conjunctions as outermost operators. So a conjunctive normal form looks like this. A disjunctive normal form looks like that, with disjunctions between the parentheses. Okay, but this is not enough. So the other question, what can we have between the parentheses? So in CNF, you can have only disjunctions inside the parentheses. For example, here you connect 3 elements inside the parentheses. Sometimes you have only 2, sometimes you have 4, sometimes you have 15. And it is also okay if you have only one element between the parentheses. In this case, of course, you don't need such a disjunction inside the parentheses. So far, do you understand this? I hope you are with me.
Yep.
Okay, thanks. So for DNF, it's the same, but the other way around. Of course, instead of disjunction, what do we have here?
Conjunction.
Conjunction, yeah, you're right. And but everything else holds. So we can have as many elements we need here in the parentheses. For example, now I have 4 elements to be connected, and it's also okay to have only one. Okay, the final piece of Lego here is this one. So what can we have instead of these dots? So there we must have, how to say, literals. Where to put this? The basic building blocks are literals. Literal can mean two things. So a literal can be either a variable, or the negation of a variable. So these are what we call literals. These are the basic building blocks. Variables or the negations of variables. So this is what you have instead of dots. For example, here you can have negation B, there, let's say C, negation A. So these are all literals. And this is how you keep going, basically. Here at the end you can have, I don't know, negation C, for example, and this is also okay. The same holds for DNF. So instead of dots, you only use literals. That's it. So these are the two normal forms we are going to learn about. Do you have any question before we start to solve an exercise?
No.
Okay, then let's go back to the previous exercise. For example, here we got this formula before I suggested to use the law of distributivity. So if you look at this guy here, what is this? Is this in CNF or DNF, or it's none of them? What do you think? So is it in CNF or DNF?
DNF.
No. No, this is not in DNF. Why not?
And
CNF is
It's
easy
CNF.
it's easy to remember
CNF.
because CNF
Big
has
Has
conjunction,
conjunction.
yeah, as the main operator. So here the main operators are all conjunctions. This is in CNF. And okay, here conjunctions connect three parts. This, the middle one, looks exactly what I just described here. So it's completely okay. Actually, how to say, we call those stuff closes. So close looks like that. It can have as many literals you want connected with these junctions. So here you have a close. So this is okay. Okay, here we have B. B is a close. This is a good question. Yes, it is, because we also allowed to use one single literal inside the parentheses. Okay, here I didn't write any parentheses, but you can just imagine that they are there. So this is also a clause with or without parentheses. It is a clause with a single literal. And similarly, not C is also a clause. So we have three clauses connected with conjunction. Therefore, this is a CNF. Okay. Okay, let's look at the other result, what we got at the end. So what do you think? Is it in CNF or DNF?
CNF.
Yes, it's
CN.
in CNF if you just imagine the parentheses at these positions, right? It looks like a CNF. So yes, it is a CNF. But I'm telling you it's also DNF. Both. Why is that? So if I use these imaginary parentheses like this one, so I put the whole formula in one pair of parentheses, then I get something like that. Actually, they call such an expression a cube. This is a this is a cube. It's, let's say, the opposite of a close. And the DNF is nothing else than cubes connected with this junction. So this is what we have here. This is one single cube. yeah, I forgot to tell you that it's allowed that we have one single cube in a DNF. Okay, now I have 3 cubes, but 1 cube is completely enough. And in a similar way in CNF, it's allowed to have one single clause or more. You can have more clauses as well. So I hope you understand that this is also CNF and also DNF, depending on how you use those imaginary parentheses. In general, I can tell you, if you have only either only conjunctions or only disjunctions in your formulas, then those formulas are both CNF and DNF. Okay, I'm going to talk about this stuff more on the lecture. So let's solve an exercise now. Let's transform some formula to CNF or DNF. Let me find an exercise. So in the test you are going to write probably in 3 weeks. You know, I told you you will write 2 tests during the semester, and I will give you grades for both tests, and from those 2 grades you will get your final grade for the course. So in 3 weeks we are going to write the first test, and in that test I will give you a very similar exercise about transforming a formula to CNF or DNF. So let's see. I'm trying to find you a more interesting exercise. I don't know. Okay, let's use this one. Okay, so let's see. Okay, so here it is, the next type of exercises. Transform the formula to CNF. And this is the formula. X implies Z or not Y implies parenthesis Z implies not X implies so many implications, not Y, you know what, sorry, not Y or not X. Okay, sorry, let me use a negation here in front of the first Z. No, sorry, don't use a negation there. Okay, exactly. Okay, So let's transfer the formula to CNF. Okay, we have to use the same logical laws as we used before. So for example, De Morgan rules and stuff. So just look at the formula and tell me what would you do first.
Remove the implication.
Remove one of the implications because we have 4 implications. So what do you think, based on your experiences, which one would be the best to pick first?
Second one.
The first one?
So the very first one?
Yeah, I think so.
Okay. Okay. Or does any one of you have another opinion?
I think the second one.
The second one, this one?
Yeah.
Why?
Because after that we can use this and or.
No, actually, the third one, the one in the middle. Yes, this one.
Mm-hmm.
I think it's the easiest one.
Okay, I see. Okay, I actually agree with the second one. I mean, I would pick the second one. This is my suggestion. Typically, it's worse to use the outermost implication first, because if you think about it, if you remove an implication, if you remove an implication, you introduce a negation. And you can hope that this negation rules out other negations at some point. If you do it in the other way around, for example, you pick the third one, so you pick an innermost implication, then it can, how to say, it's sometimes you do double amount of work because you eliminate a negation with the De Morgan law, and then you introduce a negation instead of that again. So those 2 negations would have been eliminating each other. So my suggestion is to deal with the outermost negation first, and then we continue with we proceed from outside to inside. Anyway, in whatever order you eliminate your implications, you get the same results, so there is no danger. How to say, it cannot happen that you get a different result at the end. Maybe the way will be much more difficult. So I eliminated this implication like that, and now I would like to continue with this first implication. It's a negated implication. Do you remember of a law which is about a negated implication, how we can eliminate it?
Yes, negation and use or.
I think you are talking about how to eliminate an implication. And you are right, we would eliminate it with using a or here and negation there. This is what you were talking about?
Yes.
Okay, so I'm talking about a negated implication now. So we have a very nice rule to deal with negated implications.
Is it contraposition?
It's called contraposition. This is it. I suggest you to remember this law, because it's so so common that you get negated implications. For example, if you think about it, if I remove this implication, the very last one, the left-hand side is an implication which we need to negate. So it's really common that we have to transform negated implications. So let's use the law of contraposition in both cases. So how does this work? Let's see. So if you can see implication turns into a conjunction. Of course, this negation is eliminated. And you have to negate the right-hand side of the formula. So basically this one here. Okay, so this is contraposition. Did you understand that?
Yes.
Okay, then let's deal with the second negated implication. What should I write there?
Z and X.
I can hardly hear you.
Z and X.
Yes, that's it. Z and X. That's it. Exactly. Great. Okay, so we killed all our implications. Here we can simplify a little bit further. We can remove this pair of parentheses because we have conjunction outside and inside this parentheses. So this is a little bit nicer. And and we can also eliminate one other pair of parentheses. I don't know if you can see that. So here we have this part of the formula between parentheses with disjunctions inside and also outside. Therefore, we can also remove not the whole formula, but this pair of parentheses. So basically what we got is a formula consists of 4 parts, and those parts are connected with disjunctions. So it starts to look as a DNF, disjunctive normal form. Okay. Okay, but this is not a DNF yet, because here inside this parentheses we have a very ugly stuff. So it looks like a DNF. Is it DNF already? Not, it's not, because inside this parentheses the second half is not a literal. I've told you that inside the parentheses, inside the cubes, you must have literals instead of those dots, and literals can only be variables or negated variables. In this case, it's in another form. So we have to deal with this negation.
We can remove the negation, make it like negated Z and Y.
Exactly. De Morgan rule, and this is it. And this is a DNF now. Thank you. This is in DNF, if you look at it. This cube has 3 literals, this one 2, and this cube has only 1 literal, so does this. Okay. Okay, do you have any comments or questions?
So that's it. We just like transfer it like this, and that's it.
It would be only this if I would ask you to transfer the formula to DNF. But I ask you to transfer the formula to CNF, and this means this is not the end of the story yet.
Yeah.
We are almost there, but we got the wrong normal form as the result. Actually, if you simplify your formula, you either get a DNF or a CNF at the end. You cannot know at the beginning which one you get, but you get one of them for sure. And if you are lucky, you get the one I asked for. However, you can imagine that I will intentionally ask the other normal form in the test, so to make you work a little bit more. So next time we are going to learn how to transform DNF to CNF, or in the other way around, CNF to DNF. This is a good question. Let me just give you a hint, a spoiler alert. You have to use the law of distributivity, the one we used before, the ugly law, which we only use if we really need it. Do you remember?
Yes.
Okay, so this is the point. Now we need distributivity. Distributivity is the only hope in such a situation, desperate situation. So I want to ask you to think about this. Try to use distributivity. Try to apply distributivity to this formula, to parts of this formula, and try to transform it to CNF. So this is your homework, so to say. We will see if you can solve this problem. And next week we will check out how did it go. You don't have to upload your solutions now, just bring your solutions next time and we will look into them. Okay, that's it. End of the class. So thank you guys. See you next week.
See you next week.
See you.
See you.